Hi there, and welcome back to Bringing STEM to Light. So far, what we've looked at is how vision works, and we've developed a model for how vision works. Light bounces from a source off of an object and into our eyes, and that's how we see. And we've also gone deep into an activity that is really great at disrupting the persistent misconception that something comes from our eyes out into the world, and that's how we see, called the classroom cave. And in this presentation, we're going to do some background science, and we're going to do a little bit of looking into just really what is light. The very earliest conceptions of what light were and kind of how that word light was used was really just to describe something that was bright or shiny or perhaps fiery. And we've really come a long ways in understanding what light is, even though, as you can see here, Einstein has said that for the rest of my life, I shall reflect on what light is. And it's certainly true that light is really a mystery. For all that we've learned about it and for all of the many, many applications in so many fields where we can actually apply what we've learned to be useful to us, light is still at its core, it's really still a mystery. But here is what we do know about light for sure, or at least what we think is for sure at this point. We know that light is a source of energy. It's the first source of energy, perhaps the most important source of energy. Without the light that comes from the sun, no photosynthesis, no life on Earth. So light is a form of energy. We know that it behaves both as a wave and as a particle. For a long time, there was a conversation about, is it a wave or a particle? And now we know that it is some really fascinating combination of both a wave and a particle. We also know that there are many different kinds of light. Mostly what we think of when we think of light is the absence of darkness, or maybe we think of color, because that is the light that we can perceive with our eyes. But there's a whole lot of light that we can't perceive with our eyes, and that lies on a spectrum. So we'll start with looking at the nature of waves in general, then we'll move into electromagnetic waves, which are light waves. We'll take a look at how they're related to energy, and then we'll take a look at the whole light spectrum, and then we'll see if we can answer what is light.
So let's start with waves. A mechanical wave is a disturbance in a medium that transports energy through that medium from one place to another. So an easy way to think about this kind of a wave is to imagine a couple of people standing opposite each other, and they're going to shake a rope, and they're going to shake the rope by having this first person shake her hand up and down, and that's going to initiate some energy, which is going to cause this rope that we have here to travel in the form of a wave. And what's happening is this energy that was initiated by this initial motion here is transported through the rope. So in this case, the medium that's carrying the energy is the rope, and it's traveling along here in the form of a wave from one place here to another place here. So the rope travels up and down, but stays in the same general location, and it's the energy that's been initiated here that actually moves in this direction. So here the medium is the rope, and the energy was initiated by the shaking, and it is traveling from this place right here over to this place right here. Another way to think about a wave is probably the way that you first think about a wave when you think about it. You think about a wave in water. So if you think about a still pool with water in it, and you imagine that we're going to drop a stone right into the center of it here, that is going to initiate a disturbance, much like this shaking up and down did over here. And what that's going to do is that's going to cause the energy in the water to plunk down, and then it's going to go back up, and then it's going to go down, and it's going to go up, and it's going to go down. And the way that's going to look to you is you're going to see rises in the water, and those are going to look like waves. Right? My waves are not very perfect here, but you can tell what's going on, right? So between the swells, you've got these places where it goes down, and what you've got here is this kind of a wave. Just looks a little bit different when it's in the water. And so here, the energy, again, is moving outwards, away from where we started the energy. And here it's kind of moving in a lot of different directions, right? All of them. That's kind of how the water is moving. And here the medium is water. And now imagine a person speaking, and what you experience as sound when it lands on your ear is actually a disturbance in the form of a wave that is traveling through the medium that we know as air, or our atmosphere. And so a mechanical wave is a disturbance in a medium, rope, water, air, for example, that transports energy from shaking or speaking or dropping a stone through that medium from one place to another. And mechanical waves, actually just like light waves, are described by looking at their wavelength and their frequency. So let's see what we mean by wavelength and frequency. So let's draw ourselves a wave here. Here's a wave, and it is traveling through some sort of a medium, and it is traveling in this direction, like that. And the wavelength is simply the distance from the top of one wave to the top of the other wave. So this right here is your wavelength. You could also measure the wavelength from the bottom of one wave to the bottom of the next. So this right here is also the wavelength, right? Like that. Now the frequency is the number of waves that will pass through a point in the period of 1 second. So we're going to call this 1 second in time. And we're going to have some waves here, and we're going to have a frequency, and we're going to see the number of waves that pass through is the frequency. And turns out that the wavelength and the frequency describe how much energy is transported from one place to another by the wave, right? Because that's what the wave is doing. It's taking this energy that's been initiated somehow, and it's propagating it across a distance at some rate or some frequency with some wavelength. And it turns out that the wavelength, the shorter wavelength equals a higher frequency, right? So if it's shorter, we're going to get more in the period of 1 second. If it's longer, we're going to get fewer in the period of 1 second, if that's a second. 1 second.
So here's what we understand about mechanical waves. Mechanical waves are caused by a disturbance in a medium and require a medium to travel. So we looked at a rope, water, and air. And this medium carries energy from one place to another. And you can describe a wave in terms of its wavelength and its frequency. And there's a relationship between shorter and longer wavelengths and higher and lower energy. Higher frequency, shorter wavelength, higher energy. Lower frequency, longer wavelength, lower energy. Now, light waves are different from mechanical waves in some fundamental ways. The first is that light doesn't require a medium to travel from one place to another. Light can transfer energy through the vacuum of space, and we'll take a look in a moment at how it can do that. Related to that is that light doesn't travel just along one plane, but along two planes that are perpendicular to each other. And finally, light travels at a very specific speed. All light, whether it's gamma rays or radio waves or visible light, travels at the same astounding speed of 300 million meters per second. Think about that for a minute. 300 million meters per second, that's 7 times around the Earth in 1 second. So that's how light waves are different. Let's start by taking a look at what light does travel through, if not through a medium. Rather than traveling through a medium, light travels through an electromagnetic field. A field is the area around an object that is subject to a force. So most commonly, what we're most familiar with is the gravitational field of the Earth. We are all inside the gravitational field of the Earth, and we feel and experience the gravitational force of the Earth. Magnets also create a field, and they create a magnetic field. And that field can be repulsive or it can be attractive. Well, it turns out that magnetic fields and electricity have a very intimate relationship. They are really inextricable one from the other. When you move electricity and create a current, you create a magnetic field. And so together, electricity and magnetism make up something known as an electromagnetic field. Now, this guy here, James Clerk Maxwell, in the middle of the 1800s, building on the work of many other scientists, came up with 4 very eloquent equations that, for better or worse, are beyond the scope of this course. But they define quite precisely this relationship between electricity and magnetism and light. And so while we're not going to go into the math of it all, let's take a look at an electromagnetic wave and see what it looks like. Here we have a light wave, which, by the way, is also known as an electromagnetic wave or radiation. That all means the same thing. When we talk about light, we are interchangeably talking about electromagnetic waves and radiation, all the same thing. So what you'll notice about this wave is that it's oscillating on 2 planes, and those 2 planes are perpendicular to each other, and that's because it's oscillating through both an electric field and a magnetic field at the same time. And remember, it is light because it's propagating through these 2 fields at the same time at a very specific, astounding speed of 300 million meters per second. But what's similar about this wave to all other waves is that it's defined by its wavelength and by its frequency. And the wavelength and frequency, just like for a mechanical wave, give you information about how much energy the wave is carrying. And so understanding a little bit about the wavelength and the frequency gives you some insight into all the different kinds of light that lie on the electromagnetic spectrum, which is what we'll take a look at next. Here is the electromagnetic spectrum, which is actually a map of all the different kinds of light. And what you might notice right away is that they have magnified this small area of the spectrum that we know as visible light. And that's really what we're going to focus on in this course. We're going to use visible light to study light in general. But it's a good idea to just kind of understand that as you move to the, at least on this spectrum, the way it's laid out, as you move to the right, you increase the frequency and decrease the wavelength and get more and more energetic. And so you start to see waves like ultraviolet rays, which are responsible for sunburn from the sun. And then we have X-rays, which are even more energetic and potentially dangerous, all the way up to gamma rays, which are produced by nuclear reactions and quite energetic and very dangerous. As you move to the left of the visible range, you first encounter infrared radiation or infrared light waves. And infrared radiation is what we experience as temperature or heat. Anything with a temperature, including you and me, glows with infrared radiation, but we just can't see it. Our eyes can't detect it. As you move further to the left, you encounter microwaves, which are in fact light waves that cook your food in your microwave oven. Longer waves still are radio and TV waves, which turn out to be excellent for transmitting information because they can move great distances around buildings and through the atmosphere without being interrupted easily. So that's why they're good carriers of information. And as you move beyond what we use for radio and TV waves, we've got long-range electromagnetic radiation that can have waves as long as the diameter of the Earth. So really, there's just this huge, huge spectrum. So that concludes this presentation on what is light, and I will see you in the next presentation.